Good afternoon, everybody. As we are at afternoon in Germany here. Thanks to Oracle for inviting me to speak at this summit. In the next minutes, I will tell you a story about how the challenges of industrial business and the technologies of Oracle met and mixed up to a real success. Something that we didn't think was possible until we did it. You will find some parallels to the introduction by Ranjan. It all started about 6 years ago, and I gave this speech at the Oracle Open World in 2017. I refreshed it a bit and added the changes that happened until today. But let me start with the agenda for this presentation. First, I will introduce myself, followed by an introduction of my employee. Then I'll give you an overview of my customer's business in general and of that special segment that forms the basis for our activities. In top 4, I will precise the initial situation and describe the problem we had. Finally, I will show you the use of in-memory, how the use of in-memory helped us and where we are today. Okay, let me introduce myself. My name is Thorsten Pensky and I'm still 51 years old. I made my first steps with Oracle in 1993 and it was Oracle version 6 and SQL Form 3. While studying computer sciences, I worked part-time at an institute that developed warehouse management systems, guidance systems for pallet transporter, and voice-controlled picking systems. At that institute, I had contact with Oracle for the first time, and I was on the development team just using it. Since I changed to Lufthansa, I'm working in a team that's responsible for the administration of the Oracle databases used by our customer here in Hamburg. We're doing all the things that come up when running Oracle databases like provisioning, customizing, maintenance, and optimization. In the meantime, my responsibilities extended a little bit to the organizational part of our team. Some of my hobbies are music, which means listening to it, as well as making it as I play drums in our church band, traveling as soon as it will be reasonably possible again, and scuba diving requiring the previously said. Let's have a look at my employee. I'm working for Lufthansa Industry Solutions, which is a 100% subsidiary of the Lufthansa Group. Formerly known as Lufthansa Systems, we changed the company's name in April 2015. At that time, Lufthansa Systems was split into 3 divisions. The division dealing with infrastructure was sold to IBM, whereas the other 2 remained self-contained. Actually, we have nearly 2,000 employees spread over 10 sites. 9 of those sites within Germany and 1 office in Miami. In fact, a lot of my colleagues are doing their business at the various customers' facilities. Who are these customers? Well, Lufthansa Industry Solutions is acting in several areas. Indeed, our main customer is the Lufthansa Group itself, with a part of about 50% of our turnover. The remaining part is spread among customers from transport and logistics, manufacturing, automotive, energy, media, and healthcare. On the one hand, our service includes counseling concerning strategies, processes, and conception. On the other hand, we provide research in new technologies, development, application management, and services concerning management of databases, B2B, which is especially Web Methods and Service Bus, and SAP. Let's step a little bit deeper into my business segment. Well, here's a picture showing the sites we are based. I'm working in a team of 25 colleagues at Hamburg. 4 of them working in the B2B area. 1 is working on OpenShift in a different department, while the remaining 20 people deal with databases. Beside Oracle databases, we also support Microsoft SQL databases. And about 3 years ago, we set up a cluster for MariaDB. Our scope of services includes installation and maintenance of database software, setting up and administering databases, consulting of developers and customers, tuning of databases and SQL statements, and PL SQL programming. Today, we are responsible for about 270 Oracle databases, 30 Microsoft SQL databases, and 70 MariaDB databases. Their complexity and importance varies from simple databases of some megabyte, which are used only a few times a month, up to databases of several terabyte size being business critical and used on a 24/7 basis. That means we have to provide a standby service for them 25 hours every single day of the year. Now, let's have a look at our customer's business. His primary area of work is the maintenance of aircrafts, and he does this actually at 70 airports worldwide. This includes maintenance, overhaul, and repair of about 4,500 aircrafts of 30 different types. Every single item of an aircraft can be checked, repaired, or exchanged, from a coffee maker via laboratory-occupied displays to one of 40 different types of engines or complete landing gears. The second pillar is the support for private VIP, business, and government aircrafts. Besides the complete service portfolio that I mentioned before, our customer fulfills special requests that his customers come up with. This includes cabin assemblies or upgrades that suit the taste of the customer. Moreover, the complete aircraft can be painted to the customer's request. One of the big maintenance events in an aircraft's life is the so-called D-check. This happens to an airplane every 6 to 10 years when it has completed about 30 to 50,000 flying hours. It is a major overhaul where it is nearly completely disassembled down to the skeletal structure. Even the painting may be removed to check for corrosion. Every single part is examined to decide if it needs repair. As an aircraft consists of several million parts, it takes 4 to 6 weeks and 30 to 50,000 person-hours to complete the D-check. If parts are found that need overhaul or repair, these are transferred to the customer's own workshops or to subcontractors. The big challenge is to keep track of all the parts that were disassembled, because in the end, they are all needed to put the aircraft together again. So tracking is an extremely important activity in the process. You have to know which components were disassembled and sent for overhaul or repair. You have to know where they are at a given time. Are they in transit, at a workshop, in the warehouse, or already back in the assembly hangar? Are they ready to be used again, or do they have to be replaced? In case of replacement, is the exchanged part available and where? You see, tracking is an extensive and important part of the process, and that's where our team comes into play. All the information that are necessary to keep track of the parts are bundled in an Oracle database. We call it the Trackingdb. Every activity, every move of a part is reported to the database, including a timestamp stating when it happened. These timestamps are related to different events and form the basis for further reporting. Apart from the information coming from the assembly hangar, there are a lot more sources delivering data to this database. I've outlined the most important ones. On the left side, you see SAP and the data lake. I presume that everyone here knows SAP, so I won't get into detail. Just let me say that the order management, billing, and purchase are processed in SAP. Essentially, the data lake is a mirror of a part of SAP, namely the master data. There is quite a number of databases that need access to data such as material information, for example. To avoid that every database connects to SAP to fetch the same data, we established the data lake. It is refreshed on a regular basis, and every consumer reads its required data via database links. Apart from this, timestamps are delivered from the repair shops and subcontractors, giving information about the progress, whereas the warehouse shows the available stock. All these information are bundled in an upstream staging area. There are 2 tables where the incoming data is collected and divided into keys and values. Downstream processes scan these data and distribute them to different tables. These tables represent the base of the system, the so-called business reports. Every business report represents data according to special demands dependent on the working area they are needed. Above these reports reside the aggregate reports, which mix up data from various business reports. The data for these reports are also stored in tables. Every change in one of the base tables sets an event. This event informs all jobs for the aggregate tables that have subscribed to these base tables that they need to refresh their data. All these base and aggregate tables have been moved in memory in the meantime. As most of you certainly know, users are seldom satisfied with the views provided. They have their own ideas how data should be combined to fit their needs. That's why at a fairly early point in development, they were given the opportunity to write their own views. And that's when things got worse. One might get the impression that some of them tried to outplay the others in writing the most complex SQL statement. Of course, that was all driven by a professional necessity. But it didn't take very long until the first calls came in complaining that everything is rather slow. Does that ring a bell to anyone? Let me give you some information about the infrastructure we used at that time. We had 4 HP ProLiant servers with an Intel architecture, 12 cores each, and 386 GB of memory. They were connected via 4 gigabit adapters with an HP 3 Parsan that delivered data at a rate of 587 megabytes per second. Of course, these 4 servers are distributed between 2 data centers connected via fiber channel. The operating system was Red Hat Enterprise 6. In 2017, 110 Oracle databases were distributed over the 4 servers. These were 38 production databases and 72 test systems. We used Oracle Enterprise in the versions 11.204 and 12.102. We set up grid infrastructure so we could use ASM, ACFS, and the restart functionality. A high availability is realized by using RAG OneNote, so databases can be moved between the servers without downtime. Additionally, the partitioning option is provided as well as the diagnostic and tuning pack. Later on, the in-memory option came into play. When we take a deeper look into the tracking database as it looked like at that time, we see a version 11.204. Please remember that I'm talking about the situation as it was in 2015. The database's HGA had a size of 24 GB, the PGA had a size of 5 GB. Automatic memory management was activated, and the total size of all tables in the database added up to 1.2 terabyte. Some of the tables are partitioned. On the following slide, you see an example of how a user report looks like. It's the so-called customer status report. It shall give you an impression of how user reports look like. In this case, for every customer, it shows their orders, the parts within the orders and their quantity, the date the order came in, the serial number that was received, the state of the order, and so on. The data shown in this report are retrieved from one of the many views in the database. The view used for the customer status report itself selects the data from 31 tables, 5 further views, and 3 materialized views. Its code had more than 4,000 rows. This makes it quite difficult to do performance tuning manually. But even DBMS SQL Tune surrendered when it found one of the views to select further views, which select further views. That's the point where the standard tuning methods of a normal DBL don't work anymore. We tried everything, from creating and dropping indexes of different kinds, moving tables to the key pool, and further partitioning. But with an ever-growing amount of data, all these activities were of short sustained success. The next idea was an upgrade to Oracle 12.1, as we hoped that improvements concerning the optimizer would help us. We migrated the database to version 12.102.2. The results were not as spectacular as expected. So we chose 7 typical and important views to see if we could achieve a significant improvement. One of these reports, the third one in this list, was already performing well and was chosen to see what impact the new version would have on that. You see the runtimes we had in version 11. All the numbers show times in minutes. In some areas, runtimes could be reduced with version 12, but otherwise it got even worse. That's when the idea of the in-memory option came up. We had read a lot about it, and it might help us with our problems. But as the name option says, it's not for free. So we had 2 tasks at hand. First, we had to prove that in-memory would meet the expectations, and secondly, we had to convince the people with the money. At that time, we got in contact with Sonja Meyer of Oracle and planned a proof of concept. She would join us together with Markus Bender for 3 days. Some preparations had to be done before we started with the POC. To be comparable, we had moved all other databases from the one server the tracking database was running on, so we would have as less influence from outside as possible. At the suggestion of Markus, we upgraded the database to the latest patch set. A big challenge was the usage of huge pages on the server. Never did we actually use them, nor had we spent any thought on that subject. So we talked to our colleagues from the Unix department and after some research got them set up. Automatic memory management and the usage of huge pages doesn't match, so we had to switch AMM off. As we had to think of accurate values for the memory parameters anyway, this was no problem. A more sophisticated task was to decide which tables we would move to in-memory at first. We might have used the in-memory advisor, but as we already had chosen the views we would like to investigate, we went for a manual choice. So we looked at the views in all their complexity, identified the necessary tables, and moved them in memory. And here's an excerpt of the tables as they reside in memory. In total, we moved 76 tables to in-memory, and we got a first look at the compression as an integral part of in-memory. We had moved them with mem compression for query high, which means that compression is used, but our focus is primarily on query optimization. The data you see here is retrieved from the view $im segment and shows that although we told memory we have a need for speed, compression isn't already completely put aside. The factors vary from 102, which is not on this excerpt, to 33.84, which is a real exception but highly welcome. The average overall, the 76 tables, is a factor of 3.63, which means you need less than half of the original size overall. In our case, 53 gigabyte of memory were used compared to 110 gigabyte of data in the tables. But when we put the whole output of the view under the microscope, we found two curiosities. First, we found two tables needing more space in memory than on disk. Thinking of problems during the transfer to in-memory, we removed them and started over again, but the result didn't change. We were quite confused. Then I got the opportunity to talk to Chetanka Lahiri, and he explained to me that in-memory itself needs a little bit of memory. So with small tables, this behavior can be expected. That's no problem, but you have to be aware of that. The second case were two tables of significant size that showed the same effect. Their size in in-memory was larger than the original size on disk 2. Reloading these tables didn't change the behavior as well. Nevertheless, we decided to leave them in memory. Unfortunately, we lost track of this issue as our main interest was if in-memory would speed up our statements. So we cannot really say at which point this issue vanished. We installed 2 more bundle patches in the meantime, and maybe one of them fixed that misbehavior because at any time these 2 tables were compressed as well. It didn't occur again until today, so we filed it away. Then came the moment of truth. So we refilled our mugs, took a deep breath, and started the first attempt. We started without any changes like parallelism or dropping indexes. The first results were like winning the jackpot. All but one view finished much faster than before, and we had done nothing but moving the tables to in-memory. And even those 2 reports whose execution we had to stop in version 12 because the response time was endless, returned within very reasonable times. The response time of one view was extended by 50%, but as we had just begun, we didn't worry about that. In the next step, we set all the indexes to invisible so that the optimizer wouldn't use them. To keep the prerequisites as equal as possible, we bounced the database after every test case. So most of the results were similar to the first, sometimes better, sometimes worse. Only the one view whose runtime grew within memory now even didn't come to an end. After some research, we found the reason. I'll come to this with the next slide. The next 2 tests involved parallelism. We set the degree of parallelism to 4 and tested the response time of the views again, one time with indexes, the other without. Again, we got some interesting results. In 2 cases, we got the best results we would get in all our tests. You see them in the bold figures. But in some cases, it got worse. You see the report that until now was very inconspicuous even without in-memory. Its runtime increased approximately by factor 16 to 18. And again, we had the same problem with one report not returning from its selecting travel. And this is why. Looking at the execution plan, you see a vast usage of temporary table space when dealing with a hash group by. Although only 69K were requested, the optimizer was misdirected and assumed a total of 16 GB to handle with. This was finally found to be a bug and was fixed by a later bundle patch. So no worry about that any further. In the next turn, we went one step further and set the parallel degree policy to auto so that Oracle would decide how many parallel threads to use for the best result. To the surprise of all, Oracle only used 2 different ways. Either it chose a parallel degree of 8, or it ignored parallelism completely. I put it in parentheses to show Oracle's decision. In one case, we got an extraordinary result that I also marked with bold figures. Do you remember the situation we had with Oracle 11? The performance report took 10 minutes to finish, and now it returned after just 1 second. It was so unbelievable that we repeated the test to reassure that finding, and it really did. That was really exceptional, but as you can see at the other times, not the rule. One further test was done by computing new statistics for the tables to see if that would have any impact. And in some cases it did. You can see that some response times were reduced further. So what results did we achieve? For a proper evaluation, you have to compare them with the runtimes of the version 11G because that's where we were coming from. Apart from the run report that suffered from the bug concerning the temporary table space, every runtime was cut by factors, from a small factor of 1.5 up to the incredible factor of 600. These results impressed our customers, so he agreed to invest into the memory license for the cluster. As you remember, we use a shared infrastructure. That means we're running several databases on each server, sometimes competing for the resources. So we have to keep an eye on every database and cannot let them operate to their own discretion. That's why we started without parallelism. In this way, we started without the big factors, but the results were still really good. When we had a further look at the $IM segments afterwards, we found an interesting curiosity. Although the view told us that the population of all tables had completed, there were still bytes supposed to be populated. Some investigation showed that the status of the view partially was wrong. As we moved more tables to in-memory, we reached the limit we had set for the in-memory area. Therefore, the status column was definitely wrong. It became apparent that we found another bug that was fixed with the next patch. One can get the impression that there are a lot of bugs with in-memory, but at that time, the technology was just released. It was a rather new technology, and all the bugs we found didn't have impact on the core functionality. Apart from that, Oracle was very quick at fixing the problems. Over the years, we hadn't had any failures concerning in-memory anymore. What did we learn? Well, in fact, the technology of in-memory solved our problems and still does today. And it did it in a way we never thought possible. No search for helping indexes, no query rewrite, just simply by moving the tables to in-memory. As I said before, we started without parallelism due to our shared infrastructure, but until today, we don't miss it. Runtimes have been cut by an average of 30%, and the reduction of disk I/O is an additional benefit to our infrastructure and the databases running beside this one. We could reclaim some disk space too, as we dropped several indexes. That's a nice side effect, but wasn't our primary aim. With the implementation of in-memory, we even allowed our customer to use dynamic SQL to write queries that meet his own requirements. What changed until today? Well, a lot. We replaced all 4 servers of our cluster by ones that are more powerful and with a lot more memory. A new SAN storage system was established, which allows faster access. And finally, the databases have been upgraded to version 19.10. Concerning the Trackingdb, we moved all tables to in-memory by the time. That means we actually keep more than 200 tables in memory. According to a growing number of tables and data today, we now have an in-memory area of 240 gigabytes in that database. Many more views have been created, and their complexity is far behind the status of 2015. The possibility to use dynamic SQL has become an essential part in daily work. Apart from the tracking database, we have implemented in-memory on a different one suffering from massive disk I/O generated by the access to one table. We activated in-memory, moved the table to in-memory, and were able to reduce the disk I/O of the database by 90%. And we did that just within 1 hour. Actually, we are implementing in-memory on a material supply database, but have been thwarted by COVID-19. But I think that topic will be on the agenda again soon. Let me come to the end of my speech by giving some hints. As I said before, we didn't use the IM advisor. It's not because we don't like this tool. It's great if you are to launch the technology or have no knowledge about the application. But experience has taught me that knowing the application and its purpose, you can achieve an even better performance by choosing the tables by yourself. If you can have influence on the development, that's perfect. Recently, the information reached me that with Oracle 19.8, a so-called base level was released. Tirthankar showed it in his presentation yesterday too. Base level means that you can use the in-memory functionality for free within some boundaries. The size of the in-memory area can't be larger than 16 gigabytes, for example. But hey, keeping the compression in mind, that's worth a second thought, especially as you may use it even in production. We are running a second cluster that is identical to the one we have been talking about today, apart from the in-memory option. But with the base level, we may use the in-memory option on that cluster too, and eventually don't need to move the database to the in-memory licensed cluster. Finally, one small drop of bitterness. Primarily, the tables we move to in-memory are used within select statements. Nevertheless, there is a lot of OLTP hitting the database. We're talking about up to 250,000 timestamps per day reaching the database. The population of these changes to data is done quick and never formed an obstacle. But as time goes by, it seems that DML leads to some kind of fragmentation within the in-memory area. Even if the total amount of data doesn't increase, you see a decrease in free memory. And that happens apart from the change in size caused by DML Andy talked about yesterday. Until today, the only way to solve this is to remove the tables from in-memory and reload them again. This can be done online, no problem. Actually, we do this automatically once a month, even if it wouldn't be necessary yet at the time. I must admit that I haven't checked this behavior on the latest version of 19.10, as we upgraded the database just recently. Maybe there have been some improvements made on this point. We'll see. Well, that was a short overview of how and why we got started with in-memory.